All right, Unit 10, Day 1, Parametrics. Parametrics is all about, basically, a problem that has position, but with the parameter, okay, you're adding the parameter of time. So since Algebra 1, Algebra 2, you've been working with this Cartesian plane forever, to where if we said 3 or 4, 3, the point, you know a location based off of x, y. How about if I said the point 1, 1, you know another location as far as the x, y. What parameters do and what parametrics do is that they basically grab vectors that have a direction and a magnitude, and they're going to put them on a graph that could look like this. Okay? And the two things that they associate are position, which is an x and a y. The other thing is time, which is t. So for instance, I could say something is traveling in this path, okay, and that at time 0, I'm there. At time 1, I'm there. At time 2, I'm here. So it's basically just what you've been doing with graphs as far as position, location, but now we're adding the parameter of time. And you'll understand a little bit more when we do this next problem together here in just a bit. This cheetah and this zebra problem. Now, this is the path of this particle in space, if you will. That's moving at this direction, that displaces this much amount of space in a certain amount of time. The particle could do this. It could have something like parabolic, okay? It doesn't have to be a straight line. It's just saying that it's changing position over a certain time interval. And you're tracking that, if you will. You with me? Okay, so here we go. For example, it says on the savannah, zebra heads west at 30 miles an hour. You see that vector already. West at 30 miles an hour. Real quick, what degree am I traveling at if I'm heading west? 180. Good. 180. Unit circle, right? And then it says a cheetah approaches the zebra's path going north at 45 miles per hour. Okay, what direction? You're about to have a test over Unit 9. What direction is the zebra traveling? 90 degrees. Okay? So with that in mind, it says the initial distances between the two animals are shown. Okay, so this 550 feet is that initial distance, and this 800 feet is that initial distance between where they could collide. Okay? And it says assume the two animals maintain their constant speed. So they don't slow down, they don't speed up, nothing blocks them. They are traveling at, what, 30 miles an hour and at 45 no matter what. Now what I want you to do for 5 minutes, you can do it alone, you can do it with groups, you can discuss however you want. In the space below, provide a convincing argument of one of the possible scenarios. Will A happen, will B happen, or will C happen? Go first. And then you will find the time needed. So, one that's important, very, very important, is that you're trying to find the time of when they will get to that location. They're both going to get to the intersection. No matter what, they're both going to get to the intersection. But that's not what you care about. You care about if they're going to reach that intersection at the same exact time. Okay? And look what we have here. The zebra was traveling 30 miles an hour. We wanted in feet per second, so we did dimensional analysis. Okay? And you're able to see that this hour and hour cancel. What else? The minute and the minute cancel. Then you have what? The miles and the miles cancel, so you're left with feet per second. All those conversion factors. Okay? And then it shows that the time that it took, because time is equal to distance divided by r, okay? Basically get t by itself, divide both sides by r. You get the distance is 500 divided by the rate will give you 12.5 seconds. The time for the cheetah to get there will be 12.12 seconds. So the cheetah has a faster time, so it gets there before the zebra does. And then you would know that the answer would be B. Okay? Now look, I'm going to show you something right now that you're going to use in this unit that's very beneficial for you in regards to quizzes, tests, and so on and so forth. 30 miles an hour. Let's say that I didn't want to do all that work, but I know how to get it. I'm going to show you right now something that you can use with the calculator that you can use on quizzes and tests. 30 miles an hour I'm going to convert to feet per second. Follow me closely. I'm going to press Control Divide, and then I'm going to press Control Underscore. Here's your underscore right here. Look up. Right here is your underscore. And before that I should have put 30 because we're doing 30 miles an hour. So 30 underscore MI for miles. Go down to the denominator and do an underscore for hours. And then, watch very carefully, we're going to press the blue button, which is the control button, and then this book that's above the division symbol. Then some menu is going to pop up that you can need to go all the way to the top and find this arrow. Okay, so it's this black arrow at the very top right-hand corner that when you press this, the calculator is going to convert 30 miles an hour to whatever it is that you want. What is it that we were looking for? Feet per second. Now watch this very carefully. To convert this feet per second, you need to start with a parentheses. So parentheses, Control Divide, Control Underscore, and you're going to put feet in the numerator. And then you're going to do Control Underscore for the denominator, and we're going to put S, and it converts it for you. 44 feet per second is what that conversion factor is. Okay? See, the triangle is Control Book. And then go up to the top right of that menu. So Control Book, and you'll find this black triangle at the very, very top right. Okay? If you need to look over this and go back, that's fine. Look at the video. Just make sure that if you want to benefit from using that and you don't want to do the dimensional analysis, I will accept this for full credit on the... Because think about it. Even if you did it by hand, you're going to have a calculator. You know what I mean? And there's no... I don't think that it compromises your learning by using the tool the way you're able to. Diego, did you have a question? Okay. Okay, so let's go back. So B was the correct answer on that, and now we're going to go to parametric functions. Okay? Parametric functions. Again, if you did well with vectors, parametric functions is not going to be difficult. We're just adding time to stuff. Okay? So let's go and begin with parametric functions. Very top, it says, parametric functions use a set of two functions, okay, to produce one graph. Two functions produce one graph. It almost feels like x components and y components on vectors to run the route, okay? And running the route is the resultant. So think of these graphs as the resultant, and you have an x component and a y component acting on it at the same time. So one function controls the x, we'll do that in blue, and then one function controls the y. Both functions are defined in terms of a third variable called t. Very, very important. There's your parameter. Okay? That's what links these two together. Alright, here we go. Where does this graph start? 5, -4. It does start at 5, -4, and the way I want you to know that is time is 0. The other way you know it is that's where the point starts. Where does it end? It feels like it ends the same way vectors would end, with that arrow. Okay? So now you know that the position, the x position went from 5 to 3 to 1 to -2. Each second it's changing by how much? 2. Look at this. Not a coincidence. And if I looked at the y values are changing each second. They're changing by what? By 3. They're going up by 3. So you can go ahead and put in your point and jump up by 3 each jump, or you can jump up by 2 or down by 2 each jump. The reason why I'm showing it to you this way is our last unit when we do series and sequences, I want you to start thinking about these patterns. Okay? Any questions so far what I've talked about? Okay. So let's go ahead and move on. Let's go ahead and move on to number 1. It says, note that on the graphs produced by parametric functions, the t values can be indicated next to each point. You see t is equal to 0, 1, 2, and 3. Remember how meticulous that you guys had to draw your vectors as far as the resultant was dashed, the magnitude was with the absolute value, where was the arrow, and I counted off from the homework if you didn't put arrows or if you didn't, you know what I'm saying? That's going to be the same thing here. You have to put the points, you have to put the time, and all of that stuff. Alright, so for each set of parametric functions, complete the table, sketch the graph, and answer the questions that follow. Here we go. Where do I start? Where do I start? What point do I start on number 1? 1, 2. If you don't see that, let me help you out. Y equals mx plus b. Where do I start? What letter tells me where to start? B. So if I rearranged it to look like this, you see what I'm doing right now? Oh, that's horrible. It's going to be b plus mx. This is where I start, and this is how much I jump by. This is what you've learned from Algebra 1. The only difference now is we're thinking about it like y is equal to b plus mt, and x is equal to b plus mt. Because we have two parameters, the y and the x, traveling parameters based off of time. So where do we start? Right here. So I'm looking at 1 and 2, and just be careful, it's not 2, 1. It's x equals 1, y equals 2. So let's go ahead and graph that real quick. So x is equal to 1, y is equal to 2. We are going to start right here. Very, very carefully, we're going to put time is equal to 0. Okay? Anyone, what's our next point going to be right here after 1 second, if you will? 1, 3. Okay? So, wait. No, it's not 2, 3. 3, 5. 3, 5. So, what happened? On the x, they're jumping up by 2. I started at 1, so now it jumped up by 2 to 3, and it's going to jump by 2 to go to 5, and what's the last one going to be? 7. What are the y's doing each jump? They're increasing by 3. And you can see that by this mx plus b interpretation as far as how much is it jumping each integer jump of t. So I'm going to go to 5 and then what? By 3. And then 8 and then 11. So real quick, let's plot these points. We have 3, 5. So 2, 3, 4, 5. I'm going to actually write them out. 3, 5. This first one was 1, 2. Then it was, and see, some of you are already counting. 5, 8. That's a lot to count off. Look at this. M equals y over x. Y'all learned in the last unit, the one that we were about to take a test on, is that slope is y over x. Slope is rise over run. And look at this. Rise over run has a rise of 3 and a to the right of 2. So I could go up 3 over 2, up 3 over 2, up 3 over 2, and just plot them out like that. Okay? Just make sure that you know which numbers you're looking at for that. Okay? So we'll go 1, 2, 3 over 2, 1, 2, 3 over 2. Here we have time is 1, time is 2, time is 3. And the graph looks like that. Questions? Okay. Let's go to B. Where do we start with B? 5, 8. So let's go 1, 2, 3, 4, 5, and then 1, 2, 3, 4, 5, 6, 7, 8. We're going to go ahead and put the time is equal to 0. then you guys can finish these over here. What do we have? 5, 8, 7, 11. Okay? Alright. What is my position when time is 1?
3, 5.
Okay, so you said 3, 5. Let's check them. X, Y's, we're jumping down by 2 each one. So down 2 is 3, down 2 is 1, down 2 is negative 1. Y, Y's, we're jumping down, because it's a negative 3, by 3. So 8 minus 3 is 5, 5 minus 3 is 2, and we'd have a negative 1. So if I quickly plot these, I have 3, 1, 2, 3, 4, 5. Then I have 1, 2. Then I have negative 1, 1. You have time is equal to 1, time is equal to 2, time is equal to 3. And then you could just write them out as far as their points are concerned. And it is traveling that direction with the arrow showing down to the left. What characteristics do A and B have in common and are different? What would you say they have in common? What do they have in common?
Same slope.
Same slope. What else? The same points. They both have same slope. I'll put that in quotations. And same points. What's different? They're different directions. They have the same slope, but they're going different directions, right? So, different directions. And different times of position, right? At different times, they're at a point. Okay, let's move on. Okay, so number 3, it says, what would you refer to as the starting point of this graph? Well, first let's do it. Where am I starting for time is equal to 0? 4, negative 3. Okay, so 1, 2, 3, 4, negative 3. Here time is equal to 0. Okay? And do you see how, to me, I think it's easier just to do the chart? I mean, go through instead of each individual point like this and then like this. I feel like it's inefficient and it takes too long. But you could just see the patterns by going straight down and finding them like that. Okay? What would the following 3 x values be? 1, negative 2, negative 5. Perfect. How about the y's?
-1, 1, and 3.
Yep, because you're going up by 2's on the y's, you're going down by 3's on the x's. And now quickly, we can go ahead and write these out as far as 1, negative 1 is that time 1. Negative 2, 1 is the time 2. And then negative 5, 3 is time 3. Yes, you are traveling in this direction, starting here. And yes, you could put 1, negative 1, negative 2, 1, and negative 5, 3. Now we can answer the questions. What would you refer to as the starting point of this graph? What would y'all say? 1. Say again? 4, negative 3. So 4, negative 3 is where you start. Okay. Let's see. How can its coordinates be found by looking at the set of parametric functions? Guys, when you see this, braces means the set of. And the way you're given x with t and y with t, those are parameters. Okay? So you tell me, how can you find it? Just by looking at the pair of parametrics, how can you find the starting point? Don't be afraid. It's just the constants right here. The constants that they give you, okay? So if t is 0, we could say, let t equal 0. Or, what are the constants 5 it says, what is the slope of the line formed by these functions? Can someone tell me what the slope of the line is? Careful on this. Not -3, 2. A lot of people say that. So slope is this. Otherwise, rise over run. Or the change in y over, the change in y over the change in x. Can someone tell me what the change in y is? -2. It's a +2. What's the change in x? -3. So the slope is actually -2/3. And that's common for a lot of people to say -3/2. Okay? So just be careful with that. And how can it be found by looking at the set of parametric functions? Just look at the y and do it over the x. Alright. So it's the coefficient of the y over x. Coefficient of the t values. It wasn't that bad. Shout out to Judd. Oh wait, he's here. Alright, so how can you enter polar and parametric functions into your calculator? We will, actually these are the answers to what we just did. We will explore how to actually use the calculator the next time, because it is a little bit different. I don't know why the Inspires programmed it like this, but the 84s work a little bit better as far as showing you parametrics than the Inspires. We'll talk about that next time. But are there any questions from day 1? Alright, that's a wrap. Let's do the extra credit.